neural networks. Well, let's now focus on the origins of reinforcement learning. Reinforcement learning is basically based on how humans learn, how as children we start learning, how as a human being we continue developing our skills, we build our paths. This is a journey through the fascinating history of the reinforcement learning. It has revolutionized the way we approach artificial intelligence and machine learning. Our story begins in the 16th century with Juan Huarte de San Juan. He was a Spanish physician, a philosopher, who laid the groundwork for understanding individual differences in learning and behavior. In his work, Examen de Ingenios para las Ciencias, imagine 16th century, Huarte de San Juan already explored the idea that individual differences in learning and behavior are influenced by a combination of innate abilities and environmental factors. This notion laid the foundation for later theories of learning, including the concept of reinforcement. Moving forward to the 20th century, we encounter Lev Vygotsky, a Russian philosopher. He was also a psychologist whose work focused on the sociocultural theory of cognitive development. Vygotsky proposed that social interaction plays a fundamental role in development of cognition, that learning occurs through social collaboration and communication. His ideas laid the groundwork for understanding the social dimensions of learning, which are a central topic to the concept of reinforcement learning. In that sense, we also have Jose Ortega y Gasset, whose famous studies mixed a bit between philosophy and metaphysics, covered the idea of rational vitalism, which basically explains, and it's in a nutshell, we can mention his famous sentence, Yo soy yo y mi circunstancia. I am myself and my circumstance, which basically means that what I am includes the environment where I am and the conditions in which I am. The famous Spanish difference between to be and to be, ser y estar. Following those, we have also Jean Piaget, who is a psychologist known for his work on cognitive development in children. Piaget's theory of cognitive development proposed that children progress through a series of stages as they grow, each characterized by distinct ways of thinking and understanding the world. Piaget's work contributed to understanding of how learning occurs through active exploration, interaction with the development, environment. This is key also in reinforcement learning. In the mid-century, 20th mid-century, let's say, we encounter also the renowned psychologist B.F. Skinner. B.F. Skinner, who introduced the concept of operant conditioning, is a key person in reinforcement learning and most commonly known as the father of modern reinforcement learning in psychology. Skinner's work focused on understanding how behavior is influenced by its consequences. He proposed that behaviors that followed by a favorable consequences are more likely to be prepared, while those followed by unfavorable consequences are less likely to be repeated. This means that reinforcement is key. Having something that produces benefit or pleasure will move us to learn how we can evolve to achieve our goals, while on the opposite side, negative impacts, pain, and pleasure will make us learn the steps not to achieve or the path not to continue following in our actions. Also, we have to mention that around the same time, Albert Bandura, a Canadian scientist, introduced the concept of social learning theory. This emphasizes the importance of observational learning and modeling in the learning process. Bandura proposed that individuals learn by observing others and imitating their behavior, and that learning can be influenced by the consequences experienced also by others. This idea is closely related to the concept of reinforcement learning, as it highlights the role of feedback and reinforcement in shaping behavior. Then, moving forward to the latter part of the 20th century, we encounter Richard Ernest Bellman. Some of you might probably have heard of the Bellman equation. He's an American mathematician who is often credited with laying the foundations for dynamic programming and reinforcement learning. Bellman's work on dynamic programming provided the theoretical basis for many reinforcement learning algorithms, including the famous Q-learning and also temporal difference learning. Later on in 1980s and 1990s, researchers like Richard S. Sutton and Gerald Tesauro made significant advancements in the field of reinforcement learning. Basically, Sutton's seminal book, Reinforcement Learning: An Introduction, co-authored with Andrew Barto, remains a foundational text in the field. Moreover, we cannot overlook the significant contributions of Gerard Tesauro, who in the early 90s developed TD Gaemon, which is a computer program that learned to play backgammon at a world-class level solely through reinforcement learning, which means only knowing the rules, only knowing the limits of the game, but without past experiences. All experiences were generated and learned by the program itself. Most recently, we also have researchers like Emma Brunskill and Chelsea Finn, who have been pushing the boundaries of reinforcement learning, exploring its applications in diverse fields such as robotics, healthcare, and education. So as you see, reinforcement learning has a pretty long and huge, diverse history in different sectors, like can be academics, philosophy, psychology, and of course, computer science. As we continue to explore and expand the possibilities of this powerful diagram paradigm, we honor the contribution of those who have come before us and look forward to this exciting advancement yet to come. So in this set of conversations, I think we are all have a bit in mind what reinforcement learning might look like in computer science. But just to give you a bit more of details about how to implement those algorithms. We have several scenarios in which we would like to automate the procedure to execute a task. That task might, of course, imply to have an optimal resolution. I have several examples in my mind, which I will probably describe in later on talks. Imagine, for example, we have to optimize some scheduling. You have to optimize, for example, your team in order to achieve some tasks. But you would like that your team spends the minimum hours possible to fulfill the needs for each of these tasks. And you would also like to have on those customers for whom the tasks are achieved, the best colleague from your team in order to complete it. Also, you would like to reduce the costs it takes to complete that task. Also, you would like to maybe have a shorter distance from the customer in case there's a need for a visit. Imagine that kind of problem. Well, in that sense, reinforcement learning could help you learn the policy in which to complete this schedule. But in order to have that policy, when you deep dive into the details, you would probably like to have also knowledge about the function which would optimize those results and those key objective that we're looking for. Reducing cost, reducing time, making it all in the same time frame, minimum time frame required. For that, there is a very famous algorithm, which is called null dominant sorting genetic algorithm. To You could use it. It's a mathematical combination that helps you provide solutions uh, for that optimization problem. You could also use machine learning, several algorithms to try to forecast how many colleagues, how many workers you would need in order to fulfill all those tasks that you may have. You may also need to forecast the demand of the tasks in the future. So for that, you use historical data. So that's another algorithm that you will use on just to get those insights. And I'm thinking that probably we would like to have probably a neural network. We could build a neural network in order to have a deeper understanding on those optimal solutions for our reinforcement learning algorithm. And the reinforcement learning algorithm will try all the paths in order to be able to generate the better schedules, minimizing the metrics we want to minimize and fulfilling the time frame. But let's leave it for a bit later.